I'll bet you finally feel that you are ready to do something of clear business value with your knowledge of databases. That is, answer questions about the data in a database using the SQL database query language. Of course, what you've learned about database design and definition are useful and necessary, but you'll really get a rush from discovering the secrets held within the minefield of data in the database. And yes, we finally will be doing some programming. Probably nothing like you've done before. In many ways, it will be easier programming than you might have done so far. But that ease and the power of SQL mean we can answer some pretty tough questions. This includes ones that can produce the data for customer order status questions, or even find summaries of data that give us insights about the success or problem areas of our organization. In other words, power to the SQL programmer. Hi, I'm Jeff Hoffer, one of the co-authors of Modern Database Management. This video tutorial is meant to assist you as you write SQL queries for the first time. Through examples, we will show some strategies you can follow to construct a query. Writing a query, like writing a program in any computer language, is an iterative process. This process may iterate because you make errors in your first attempts, or you adopt an approach of writing the query in pieces, and the whole query does not come together until you have tested each component part of the query to get it working correctly. So, if you have programming experience, draw on strategies you learned about problem solving, such as decomposition and testing, to help you in SQL query writing. You should find value in this video before you begin reading about SQL in the textbook, or during your first reading about SQL. The examples in this video are simple, involving just one table of data. A second SQL video tutorial shows queries that are more complex, involving multiple base and derived tables. Before we illustrate some processes for SQL query writing, it is worthwhile to summarize the purpose of each clause of a SQL statement. Select. This is where we list the attributes, aggregates, or expressions to be displayed in the result or answer table. The From clause, here we list the table or tables, real, derived, or views, where the data needed to produce the select list are found, and may be where we specify how to link tables from foreign keys to primary keys. The select and from clauses are the only two that are required, but there are other clauses that are often needed. For example, the where clause qualifies which rows from the tables in the from list to use to produce the select list results, and maybe to specify how to link tables from foreign keys to primary keys. Group by allows us to specify categories or groups for which to show the select list results, and hence on which to compute aggregate values. Having is used to qualify which groups to include in the select list results when a group by is used. And order by is where we specify the sequence in which to display the rows in the result or answer table. When given a query to write, your basic task is to determine which clauses are needed and what elements need to go into each clause. In this video, we'll work some examples to illustrate this process, and we'll show several approaches as the queries become more complex. We'll also illustrate a few idiosyncrasies that can trip you up. There is no one approach for creating a SQL query to answer a question, but there are various techniques you can use to help you figure out how to construct a query. Some techniques are simple, in which you basically parse the question being asked to translate it into SQL elements. Other techniques involve drawing diagrams or writing logic statements in pseudocode, which can then be converted into SQL clauses and elements. We'll begin with a very simple query. This query is list salesperson name and telephone number for all salespersons who live in Florida or New York. Is it possible for a salesperson to live in both Florida and New York at the same time? A really good salesperson could own a permanent residence and one or more vacation homes from their commissions for their selling. Well, whether we handle this depends upon the database design. When figuring out the structure of a query for even a simple question like this, it is essential to have handy an ERD or the data definition language of the database. From this question, it would appear that we want data about salespersons. We are using SQL Assistant Web Edition from Teradata to process our queries, and the user interface shows in the pane on the left the tables in the database. Let's open up the salesperson table. And we'll look at the columns. And see if the attributes we want are in the table. We see that there is only one attribute for the state of a salesman. So it appears that the database records just one salesperson address, including state, at a time. Of course, the more we know about the meaning of data in the database, beyond what an ERD can tell us, the more likely it will be we can construct a query that really answers the question being asked. The question mentions salesperson name and telephone for display, but also implicitly mentions state because of the qualification of where salespersons live. We see all three of these attributes are in this one table. The select clause lists the data we want to display, in this case salesperson name and salesperson telephone. So let's enter this part of the query. So we'll put in select salesperson name and salesperson telephone. And we know we are using the salesperson _T table, so we know what needs to be in the from clause. That is salesperson _T. The question says we care about salespersons who live only in Florida or New York. Thus, we want to limit which rows of the salesperson table to display, only those where the value of salesperson state is Florida or New York. So in this case, because we don't want to work with all the rows, we need a where clause to specify the rows we want to include or exclude. It will be easier to specify which we want to include because there are only two states to include. There are several ways to write the where clause. One approach is to use Boolean set logic. Let's take a look at what the query is asking by representing it as sets. Consider the set of all salespersons. The query says we are interested in Florida salespersons and also New York salespersons, which are mutually exclusive subsets. A salesperson has only one value for salesperson state. But we are interested in combining the subsets, which we do with the Boolean operator OR. Sometimes we'll use the term union to combine sets rather than OR, but for our purpose here in a where clause, OR is the right choice. Implicitly, we are excluding all other salespersons not in Florida or New York at the time the query is executed. We can translate this set logic almost word for word into SQL in the following where clause. Where salesperson state equals Florida or salesperson state equals New York. Pretty straightforward once we understood the subsets involved. Each part of the where clause defines each subset, and the OR operator says how to combine the two sets. Notice anything special about this where clause? Well, first you see that I used the standard two-letter abbreviation for state names. I know this from having looked at the data before, even though the data definition language here says that it is character 20 long. Second, notice that I had to repeat the attribute name salesperson state in defining the criterion for each subset. SQL requires that every part of a compound where clause has to be a full qualification. Each part separated by an or is called a conjunction. Now we have a complete query. So let's execute it. And we see 4 salespersons who satisfy the condition. Are you sure we wrote the query correctly? Yes, we got an answer, but how do we know if we got the right result? Maybe we wrote a query that is free of any SQL syntactical errors, so it produces a result, but not the one we intended. Well, there are several things we could do to check out our work. First, we could visually scan the salesperson table to see if we, by brute force, manual means, can find the same result. This works fine for relatively small tables, but can cause real eye strain and headaches for large tables. We can scan the table produced from simply select salesperson name, salesperson state, from salesperson. And let's see if visually we find these same 4 salespersons. So what we're running is an unqualified select. And when we do this, we verify that our query did in fact produce the same results, because we see Robert Lewis, William Strong, Pepe Le Pew, and Mary Smithson as the only salespersons in Florida or New York. Another way to check that we have an accurate query is to write the query in a different way, but still in a way we think answers the same question. If we get the same result, then we may have written a correct query. Some people complain that it is possible to write SQL commands several different ways to compute the same result. One reason they complain is that some of the alternatives may very well be inefficient in using computer resources, writing the so-called query from hell. As you become more experienced, you'll care about computing resources. For now, as a novice, you'll be glad there are different ways to write the query based on several equally accurate views of what the query is asking. For more complex queries, you might have to attempt to view the query from several different perspectives before the light bulb turns on and you discover a correct way to solve the query. For this query, there is an alternative, and actually simpler way to write the where clause. We'll leave the select salesperson name, and remember we want salesperson telephone from the salesperson table. In this case, our where clause will be where salesperson state in, and then we provide a set of values. This is an approach that many SQL programmers prefer because, as we'll see later for more complex questions, this is a more generalizable approach, and one that also takes advantage of SQL's set orientation. What this where clause says is pick the rows where the salesperson state values is any value in the set of values provided. In this case, the set includes only Florida and New York. There are implicit OR operators between the values within the parentheses. And when we execute this modified version of our command, we should get, and we do, the same 4 salespersons. Another way to check that we've got an accurate result would be to write a different but related query to make sure that the rows shown are only for Florida or New York. I could do this by adding salesperson state to the select list and rerunning the query. So let's do that. And we would expect to see only Florida and New York for the salesperson state values, which we do. A combination of these and other methods can give us confidence that our query actually answers the question that was asked. Now, let's look at a query with a little more complicated set of conditions. This query is list material name, material, and width for raw materials that are not cherry or oak and whose width is greater than 10 inches. Well, let's look at the raw material table to make sure all the attributes we need, material name, material, and width, are in the table. Yes, they're all there, so this is the only table we'll need. And the select list and from clauses should be easy to write now that we've seen the first example we did. These clauses will be select material name, material, and width from the raw material table. Now let's break down the qualification part of the question. We'll do so as we did before with a Venn diagram. Natural language statements can be vague and imprecise, but a Venn or set diagram will be clear and exact. Of course, we have to make sure that the set diagram means exactly what is meant by the natural language question. We'll start with a circle for all the raw materials. The question mentions raw materials made of cherry and made of oak, which must be disjoint subsets. So we'll draw two separate circles for those categories of raw materials. And the query qualifies raw materials that are greater than 10 inches in width. So let's draw a third subset of raw materials for this qualification. But now, this subset can overlap with the other two circles. So, which part of the diagram do we want? Now, this depends on how we parse or group each component of the qualification. Let's assume that we want those materials that are not in the cherry or oak circles, but are in the width greater than 10-inch circle. Finally, you found a use for that finite math course you had to take. We can translate this diagram fairly straightforwardly into SQL as follows, where material not in the cherry or oak subsets and width greater than 10. So in other words, it is in that subcircle. Now we'll run the query and get the result. And the result happens to have 260 rows in it. Alternatively, we could have written the where clause without using the in operator, and we could have written it this way, where material is not equal to cherry or material not equal to oak and width greater than 10. Would this work? Well, actually no, because we wouldn't be combining the right subsets. For example, the first part of this where clause would include raw materials made of oak that are wider than 10 inches. When using multiple ors and ands, it is good to get in the habit of using parentheses to make it clear how to process compound conditions. SQL works top to bottom, first doing ors and then doing ands. It will do operations within parentheses first. So we'd have to modify what we just did as follows, by putting parentheses around this compound or condition. The part of this where clause within parentheses is equivalent set logic to the not in version we wrote earlier. When we execute this query, we'll get the same result that we did before. But isn't the form with not in a lot clearer? The last query we're going to work on illustrates some other features of SQL we can even use when only one table of data is involved in the query. The question for this query is, which product finishes have more than 3 products of that finish? And how many products are there of that finish? Well, it looks like we need the product table, so let's open up that table in the directory. And we see that one product characteristic mentioned, product finish, is included in the table. So it looks like this is the table we're going to use. Thus, our from clause is clear. It is from the product table. Yes, we don't have to write the select clause first. We'll add that clause as the first element of the query later, when we know what to display. To begin to understand this query in more depth, let's draw a sample set of rows for the product table. The question mentions product finishes, so we show multiple rows representing the products of different types of finishes, such as oak, cherry, and so on. Because the question focuses on product finish, let's reorganize the table, so all the product rows for the same finish are next to one another, forming subsets of the table based on product finish. Let's look at the question again. It says which product finishes, not which products. That is, we want to show a characteristic of the subsets, not of the products directly. And what is that characteristic? It is the number of products in that subset. That is, we want to display 2 characteristics of each group. The finish, common for all rows of that group, and the number of rows in that group. SQL has a function to count the number of rows, which is not imaginatively called count. We say count star because we want to count the number of rows. So the question indicates the select clause of select product finish count star or asterisk. But we still haven't told SQL that we want these values to display for each subset circle. That is, we've not told SQL the criterion for subsets or groups. Actually, if we ran the query now, SQL would give us an error message because product finish is a characteristic of a row and count is a characteristic of some undefined group. And all the elements we want to display have to be at the same level of aggregation, either all row level variables, as we've seen in previous queries, or all characteristics of the same group or groups. Thus, we have to tell SQL that we want these values to display for each of the subset circles or groups. We do this with a clause to define the subsets or groups, and again, the SQL wording is a lot like our natural language, which is group by product finish. Now we have a query we could execute, but if you look at the question, we have not accounted for one more element of the question. That is the qualification that we want to see the finish and count only for subsets with more than 3 products or table rows in them. Before, when we saw a qualification, we used a where clause. A where clause tells us which rows to include in the query, but in this case, it isn't rows we want to include or exclude, it's subsets or groups. The equivalent clause for qualifying groups is the having clause, which for this question would be having count asterisk greater than 3. Now we have a complete query. We know what to display, shown in the select list. We know where to find the data we need to display or to compute what we need to display. That's shown in the from clause. We know how to create subsets of data needed for the computation of count. That's shown in the group by clause. And finally, we know which subsets to include, shown in the having clause. Now, we'll execute the query and get a result showing exactly one product finish, oak, which satisfies the qualification. So there is only the one that satisfies the qualification. We could, of course, scan the product table to verify this. I've done that, and I know that our query is correct. There are many more single table queries we could illustrate, but hopefully these examples have shown you some strategies for constructing simple SQL queries. Please read again the first chapter on SQL to see other examples and to learn about other features of SQL we didn't illustrate, such as the order by clause for sorting the rows in the result table. In this video, we worked with only database tables, or what are called base tables. In the first SQL chapter, you see that we can simplify complex queries by first creating from multiple tables a view, which is one virtual table, and then writing a simple query on that view to produce the final result. It is comforting to know that you can't damage a database by querying it. So don't be bashful about writing a query. If there is something that SQL can't figure out, SQL will slap you in the face with an error message, which may be able to help you determine where you went wrong. In many cases, however, the error messages from a SQL language processor are cryptic and terse, maybe like some answers you get from your student loan officer, and give you only minimal clues to what was wrong. Thus, it is best to use the strategies we suggested in this video for testing a query and for thinking about the query in sets as you construct the query. It is important to become proficient with simple queries in order to be able to write the more complex ones involving multiple tables. Often multiple table queries, those involving data from several tables or the same table in multiple rows, can be broken into parts for which each part involves a single table query, and the parts are combined to answer the more complicated question.